Welcome to episode 264 of CppCast, the first podcast for C++ developers by C++ developers. I'm your host, Rob Irving, joined by my co-host, Jason Turner. Jason, how you doing today?
I'm doing all right, Rob. How are you doing?
I'm doing good. Looking forward to virtual CppCon next week. How about you?
Yeah, right. Monday that starts, huh?
Yeah.
I am, or technically Sunday is like,
The
it
training
reads like there's
courses.
like, no, there's still like a meet and greet effectively on the
I didn't
calendar.
realize. Okay.
Something like that. And I'm like, I don't really know what that means. I might not be able to join in myself because I'm going to be busy Sunday, but
Okay.
Yeah, the training courses have already started.
Oh, wow. Okay.
Yeah, they're the week before instead of the weekend before.
That's interesting. Okay.
yeah, and they were adjusted to make sense for time zones and
Right.
people's availability and all that stuff too.
So this will be very interesting to see how a virtual conference works.
Yeah.
It certainly will be.
I mean, and
Hopefully it
it's
goes well.
Oh, sorry, Rob.
Go ahead.
I was going to say, in a way, CppCon gets the advantage of not being the first one, right? Because there's already been like 4 or 5. So they get to learn from everyone else's mistakes, hopefully.
Yeah. Okay, well, at the top of the episode, I'd like to read a piece of feedback. We got this tweet from Kobe last week. Great episode and fun to listen to. This is in response to our unit testing episode with Oleg Rabiv. And yeah, great episode, fun to listen to. Sometimes I'd use this CPP member accessor library to poke around non-public interface and members. It makes it easier versus extracting something inherent in the class type. Method is based on a few articles, one of them from Herb Sutter. And I'll put a link to this in the show notes, but it's a way to, get at private members without just changing, the public-private definition we talked about last week.
Right.
Yeah.
I saw this thing.
Mm-hmm.
I don't remember when.
I think it's the first time I've seen it. It's interesting, though.
Maybe I'll have to take another look. Yeah.
Well, we'd love to hear your thoughts about the show. You can always reach out to us on Facebook, Twitter, or email us at feedback@cppcast.com. And don't forget to leave us a review on iTunes or subscribe on YouTube. Joining us today is David Olsen. David's first job out of college in 1993 was working for several years on the front end of the Rational Software C++ compiler. Then he didn't touch C++ at all for a couple decades, instead programming mostly in Java and C#, working on various software development tools and mobile apps. For the last 4 years, David has been the lead developer on the PGI C++ compiler, recently renamed to the Nvidia HPC C++ compiler. He has been a member of the ISO C++ Standards Committee since November 2018. David, welcome to the show.
Thank you. I've been listening to this podcast for several years. I'm glad to be a guest.
Awesome. Long-time listener, first-time guest.
Yes.
I'm curious. I don't think I'm at all familiar with Rational's C++ compiler.
It was not a success. Pretty much nobody heard of it. We had very few sales.
I guess that
Mostly used
explains
internally.
why you changed over to Java and C# for a while.
Yeah, I was moved off to, it was shut down and I was moved to other projects.
1993, huh? Back in the era when you could still charge for a compiler, basically.
Yep.
Okay, well, David, we got a couple news articles to discuss. Feel free to comment on any of these, and we'll start talking more about the Nvidia C++ compiler you're working on, okay?
Okay.
All right, so this first one is on Herb Sutter's blog, and this is C++ 20 approved, C++ 23 meetings and schedule update. So yeah, the big news, I saw this over Twitter and on Reddit over the weekend, is that C++ 20 has passed unanimously and is on track to publish later this year, which I think we were all expecting, although maybe there was some concern that, with the virtual meetings and the pandemic that things might not go as planned, but it's certainly great news that C++ 20 seems to still be on track and getting published soon.
Yeah, the pandemic didn't affect the publishing. The committee finished all our work, technical work,
Right.
at the final face-to-face meeting in February. So this is just waiting for the countries to approve their
Accept it.
ballots.
Right.
I think, to me, the most interesting news from this, because I wasn't at all concerned that C++20 was going to ship at this point, was that all future face-to-face meetings have been postponed tentatively, right? So Kona, the first one that I actually bought a ticket to and was planning to go to, has officially been canceled, I guess, right?
Correct.
Yeah.
But that's fine. I will still go to Kona.
So yeah, everything's canceled at least until the end of March. And then, hopefully after then, things will be in a state that they can start picking up again.
Well, Herb, in other communication to the committee, has said he thinks it'll be a long time before
Really?
Yeah, these international committee meetings will be one of the last things to get back to normal.
Okay.
It does seem like one of the more risky things because you're asking a bunch of people from different parts of the world to come all together into a room with 200 people again or something.
Correct. Yeah, it's that gathering from around the world that is a problem.
Should just do it on a cruise ship.
Oh, God.
So yes, the committee is trying to figure out how to make progress virtually without these meetings.
How do you think it's been going as a member of the committee?
It has slowed down.
Mm-hmm.
And so while we still plan to have C++23 and we still have the same priorities, there's a good chance we won't accomplish as much as had originally been hoped.
Right.
Yeah, so that's one of the key points also from this article is, 23 and 26, whatever, 29 are still going to happen. It just won't be necessarily all the features that were hoped for, right?
Correct.
Yeah. Okay. Next article we have here is a post on the Stack Overflow blog, and it's if everyone hates it, why is OOP still so widely spread? And this is kind of interesting. It goes into the history of object-oriented programming and kind of theorizes that, OOP might not be that popular on its own merits, but it might just be kind of piggybacking on language trends. Right, Jason?
Yeah, I thought it was fascinating. Effectively, to some extent, this article blames C++ for making OOP popular.
Right. Yeah, and Java as well, since Java kind of even doubled down on object-oriented programming and became very popular at the time.
Yeah, and meanwhile, C++, from our perspective as C++ developers, like, whoa, hold on a minute here. No one ever said C++ was exclusively an object-oriented language. That's just one of the things it can do.
Yeah. Do you have any thoughts on this, David?
Yeah, I haven't done much UI programming, but when I have, it's been object-oriented, and at least in those situations, I found that object-oriented works pretty well. So I think object-oriented program has its uses. There's some domains where it's a good fit for the problem, for the programming. And I think it'll always have a place. It'll always be around.
I feel like for anyone who's curious to dig into what you just said, you can do an apples-to-apples comparison here with GTK, which is the C GUI toolkit from, the GIMP to GUI GIMP toolkit or whatever, and GTK-MM, which is the C++ wrapper around it. And GTK-MM is like 100 times more usable than GTK because the things are actually organized into classes and objects.
Makes sense. Okay, and then the last article we have here is on the Visual C++ blog, and this is about new safety rules in C++ Scorecheck. And I think it's probably been a little while since we talked about the core check, but they're adding some new stuff here, checking for having a default case in your switch statement, expensive copies with the auto keyword. So it's all good stuff.
Yes, I like that. I like that they're finding potential problems and warning about them, and especially like that. At least in 3 of the 4, the warning message contains a suggestion of how to fix it.
Yeah, that's very nice.
I also found it very interesting that in, I think also 3 out of the 4 of these or so, the counter example is Rust. Like, look, Rust won't let you do this, basically.
Yeah, I thought it was interesting how they talked about Rust in here because, there's still no support for Rust with Visual Studio, but interesting way to, show how another language handles these things.
Yeah.
Yeah.
I asked people on Twitter recently, what's your favorite non-C++ programming language? And a considerable number of the answers were like, you mean other than Rust?
Okay. Well, David, we talked a little bit about stdpar and the Nvidia C++ compiler a few weeks ago when we saw a blog post, I think from you. Could you start off by telling us a little bit more about it?
Okay, the Nvidia HPC C++ compiler.
Mm-hmm.
Oh, sorry, let me go back a bit. PGI, Portland Group Incorporated, has been around since the 1989 with a Fortran C and later a C++ compiler for high-performance computing. We've been recently rebranded to the Nvidia HPC compiler group.
Okay.
And so yes, our market is high-performance computing, especially the scientific computing on the supercomputers. And our big project of the last couple of years is getting the C++ standard parallel algorithms to run on GPUs.
Okay.
And so we have come up with the term stdpar stands for standard parallelism, which is any construct in standard language that'll get you the parallelism. So in C++, that's the parallel algorithms that were introduced in C++ 17. Fortran recently introduced a standard parallelism, the do concurrent loops.
Yeah.
So we're using stdpar to refer to that too. We think that will be useful. Yes, our group we still produce a Fortran compiler, and a lot of people use it. There still is a lot of Fortran code out there in the HPC market. So yes, we introduced it this year, feature of running standard C++ code on GPUs.
And now,
using the parallel algorithms.
Okay, so it exclusively applies to the parallel algorithms.
That's the only mechanism for parallelism in C++. So yes, that's what we latched on to get the code onto GPUs. GPUs are good at running code in parallel.
So like a std thread, I'm saying that's not going to automatically ship off to a GPU or something, just to clarify.
No, and that's not a good choice to put on your GPU.
Just making sure we were on the same page.
Right. GPUs are best when you run the exact same code in multiple threads, where the threads are running the same code, just on different data.
Okay.
And so yes, you want like one of the algorithms where each iteration you can run in a separate thread, but they're all running essentially the same code.
So from the programmer's perspective, what does this look like? I'm using a standard algorithm. Do I do anything special?
You just write standard C++. And well, to get it onto the GPU, you use the Nvidia compiler, NVC++, with the right option to turn this on.
Okay.
And it will take any algorithm that you've used a parallel execution policy with, and it will run that on the GPU.
Okay. Sounds very easy to use then.
It's almost too good to be true.
It is easy to get going, but there are some limitations which are inherent with GPU programming.
Okay.
Do you want to go into those? Yeah.
Yeah, I will sort of. Right, GPUs are not just CPUs with more threads, and they've always been difficult. They've often been hard to program. Look, they have a different instruction set, so the compiler has to generate different code to run it on the GPU. And GPUs have separate physical memory. They don't share the same memory banks. So you have to worry about getting your your data from the CPU memory to the GPU memory. And that has always, those have always been, or usually been done explicitly. In the early days of GPU programming, the programmers would have to specifically say, here, I want this function to be compiled for the GPU. And then you have function calls to your runtime to move the data, to explicitly move data between the CPU and GPU memories, so it can be available on the GPU for your code.
Mm-hmm.
So in stdpar, we are working on eliminating or reducing those limitations, try to make it easier, but we can't quite get rid of all of them right away.
Is that a limitation of the C++ memory model or the hardware capabilities or something else?
Well, the limitations come from the GPUs.
Right.
Removing the limitations from, or hiding those limitations from the programmer is just a lot of work.
Oh, okay.
It takes coordination with our compiler, with our runtime, with the driver team. So everyone needs to cooperate. From the operating system, we need to make changes to Linux to get some of the memory to remove some of these memory limitations. So what we have accomplished, and the limitations that we have gotten rid of, the compiler will figure out which functions or lambdas or which code you want to run on the GPU, and will automatically compile that for the GPU. So you don't need to explicitly say, I want this function compiled for GPU. So there's no host or device annotations on your functions.
Okay.
For memory, we have arranged through work that Nvidia has done for the we've arranged so that all heap memory, all dynamically allocated memory, is available on the GPU without you having to do anything.
How does that work?
Yeah.
Actually, the compiler intercepts calls to the allocation routines the operator knew and allocates it in a special way. It basically informs the driver for the GPU, hey, this memory make this memory available. And then the GPU driver it'll use page faults to automatically copy the memory as necessary. So it'll detect the first time you access it from the GPU and do the copy then, copy it over to the GPU memory.
Kind of sounds like how memory checkers like address sanitizer also work, having to kind of hook into these things. Maybe it's not.
Sanitizers would want to do similar things like hooking into page faults and seeing when you access.
So I feel like whenever I go to upgrade my computer, I can never keep track of like PCI Express 4.0 3x with 16 lanes. I don't even know. Like how much overhead is it to be sharing this memory between the main memory and the GPU?
There's some. It depends on the application.
Okay.
We have many programs where this managed memory, as we call it, or unified memory, is just as fast or is about as fast as if you moved the memory yourself explicitly.
Okay.
But there are others where it's significantly slower.
So it is something that you might have to be aware of if you're sharing lots of data.
Right.
Okay.
So this is one example of sort of the performance productivity trade-off, which we see. So this stdpar feature, this automatically standard C++ on GPUs, is going for productivity.
Mm-hmm.
Okay.
We think this is one of the most productive ways to get good performance. But because standard C++ does not have any mechanism for fine-tuning fine-tuning the details of how you run these algorithms in parallel, we have to make assumptions and go with things that work generally. There's no no way to specify the data movement. So that's why we have to use this unified memory.
Right.
To get the very best performance, you will sometimes want to do this fine-grained control. You want more control over how things run. And so you would have to use some other programming model, like OpenACC or OpenMP or compiling in CUDA.
Okay.
So CUDA is Nvidia's sort of programming model they've had from the beginning for programming for GPUs, which gives you absolute complete control over everything. So you can get the best performance by programming in CUDA, but it's at the cost of more work and less portability.
So you said the compiler detects which functions we're calling and tries to automatically handle that. Is there any limitations in the kind of functions we can pass to our parallel algorithms?
On the GPU, there's limited access to the operating system.
Okay.
It really does not have access to the operating system, except for limited ways that we provided. So if your function's doing I/O,
right.
that won't work.
That makes sense.
We can compile it for the GPU, but it won't work.
Okay. What does the failure case look like, actually? If I ask it to do something on the GPU and it can't, do I get a compile time error or runtime? Or?
Sometimes you get a compile time error. Sometimes it's a runtime error.
Okay.
Better error reporting is an area we need to work on.
Okay. At the moment, though, I mean, that's understood. It sounds like a very difficult problem. Is it an error that I can catch in some way with an operating system signal handler or standard exception or something like that?
No. Actually, if you're using the parallel algorithms, the definition in C++17 for the parallel versions is if any exception escapes, then terminate is called.
Oh, okay.
And so that's what we do. We have in our implementation, if anything goes wrong,
Terminate.
if the GPU kernel fails, then we call terminate.
It's better than corrupted memory and continuing on or something like that.
Right.
I know there's different execution flags with parallel algorithms. How do those work with stdpar?
Okay. C++17 introduced 3 execution policies for the parallel algorithms. C++20 added a 4th. There are now 4 of them. Seq, S-E-Q, stands for sequential. That means no parallelism. Unseq really means vectorized. Okay. But some people objected to the name vectorized or vectorization, so it's called unsequenced. And then par stands for parallel. So just run this in parallel. You can run it on multiple threads. And then par unseq says it's safe to do both parallel and vectorized. And the vectorized one, the unsequenced, has more restrictions on the code in question because you can run multiple instances, multiple iterations of your loop on the same thread at the same time interleaved. So if you're doing unseq, one of the unsequenced ones, you can't use any locks inside your code. For the parallel ones, you have to avoid data races. It's up to the programmer to avoid the data races. The compiler. So you have to be careful about what each iteration of your loop accesses to avoid data races. Right, so those are the 4 execution policies that you can apply to these algorithms. In our stdpar implementation, the 2 parallel ones, par and seq, we will run those on the GPU.
Okay. So you will not do sequential execution on the GPU?
No.
Okay.
That would make sense,
right? There's no point. There's not a benefit of doing sequential execution on a GPU.
Right. Someone we had on a long time ago, Rob. Now, I don't even remember who it was. We were talking about the parallel algorithms, and our guest suggested that we should treat every algorithm call as if it were a parallel algorithm call and always pass one of those execution flags to it, and then just let the runtime or the compiler decide what to do in that case, if it's enough data to parallelize it or not, or if we specify that it can't be. I was just curious if you had an opinion on that since you are been working on these things.
Auto-parallelization is quite hard. It's hard for that's still a little bit beyond what compilers can do.
Okay.
Right. Detecting the potential data races is a very hard problem. I think that's where programmers still earn their money. Is finding or avoiding problems like that. PGI has tried auto-parallelization in the past in their OpenACC, and it's not something we have continued to pursue. I think
okay.
we're not quite ready for that. So it may make sense as you write your algorithms, you can look at every one and say, okay, if this one is safe to parallelize, I may as well throw in that par policy.
Right.
And let the compiler parallelize it if it can. But you got to be careful that you don't tell the compiler to parallelize one that would be unsafe, that would result in a data race.
Right. And I guess if we took that standpoint, then we would be ready to roll as soon as we wanted to compile with NVCC.
Right.
It's interesting. It's like future-proofing your code in a sense, if as you say, you can know whether or not this algorithm call can be parallel. Right,
but you got to watch out for those other limitations that are, say, specific to the GPU. So I talked about the memory. The heap memory is automatically shared.
Right.
But that means stack memory or global memory is not. And so if you try to access a stack variable from within your parallel algorithm call, and we put that on the GPU, that will fail.
Oh, okay. That would be easy to accidentally do.
Yes.
Or at least unintentionally with a reference capture and a lambda or something.
Exactly. That's why in my presentations I put that. Watch out for reference captures.
Okay.
In your lambdas.
But if I pass a lambda in with a copy capture, that's fine because that's part of the function state?
Yes, the lambda object, the capture itself gets actually copied because it's passed to the function. It actually gets copied to the GPU memory. So there's a separate copy of the lambda capture in GPU memory, and that works fine.
Interesting. Okay. Yeah, I mean, I guess if you were doing a reference capture into a lambda that you're passing into a parallel algorithm, you're probably already asking for trouble because you're probably doing some unchecked access on it, right? I mean, not probably, but there's at least a good chance.
It depends on whether you're modifying it or you may have used a reference capture just because it's expensive to copy.
Right.
And you're only reading it. And that would work in a CPU multi-threaded environment.
Right.
It just might have problems on the GPU.
Might have problems. Okay, cool.
So I actually have used, in some of our example code, some of our code we've used capture by reference, but for something that was expensive to copy, but we had to make sure that the object itself was on the heap.
Okay.
I know you mentioned Linux. Is that currently the only supported platform?
Yes.
Okay.
We are the Nvidia HPC SDK is Linux only. So we support a variety of CPUs, x86, Power, and ARM. We are working on a Windows port. Windows version will come sometime.
Okay. And what types of GPU hardware are supported? Is it kind of only the latest and greatest from Nvidia?
For stdpar, yes, it is Volta or newer. Volta was released 2 years ago or 3 years ago. With some support for the earlier architecture, Pascal, but to get the full feature, you need to be on Volta or newer. The other GPU programming we support Other ways of other GPU programming models, we support all the way back to the oldest ones. So if you're using OpenACC to get onto the GPU, then yeah, we support older ones. But the stdpar is just the newer ones because the Volta was the first one to have independent thread scheduling, which is what you need to sort of guarantee that the parallel algorithms will work.
Okay. I'm sorry, I had to look up Power because I'm like, Power, I know I'm supposed to know that. That's IBM's architecture, right?
Yes, that is IBM's CPU architecture.
Okay, so I feel like I see a theme here. If you say x86, ARM, and Power, you are specifically aiming for the supercomputing world, then, it sounds
Correct.
like. Okay.
Yes.
What kind of response have you gotten since introducing the Nvidia C++ compiler? I mean, I'm sure there's lots of programmers out there who are used to using something like CUDA and having full control, but are they more interested in getting the productivity by using stdpar?
Many of them are. We think people are still trying it out. Mm-hmm. We haven't had a whole rash of bugs. We've had enough bug reports that we know people are trying it.
Okay.
But not enough to make us worried. The GA release, first one, was only in July. So it's only been out there, easily available for a couple months.
Oh, wow. Yeah, I mean, if you're not getting very many bug reports, the other option is that the system is perfect and there's no bugs for people to report.
Right. I know that's not the case. So. But our messaging is that the parallel algorithms are a good way to go for new code,
right,
and new projects. If you have existing code that runs on the GPU with some other programming model, don't go try to change it.
Okay, so if you're already
if it works to your satisfaction, so this is right. So this is aimed at newer projects.
Okay, so if you're already having success with CUDA or something else, don't try switching.
Correct.
Okay.
And you may find, so we encourage it for the productivity reason. We encourage you start with standard C++, mm-hmm. and measure your performance. So that'll get you the best productivity, the best portability. And in many cases, we think the performance will be good enough for your environment. But if you need better performance, then you can move on to other programming models. You can mix in OpenACC, may get you some. If you need the best performance, then you can rewrite just the core parts of your program that need the performance. You could rewrite them in CUDA.
Okay, so if you said it's only recommended for new code, if I'm already using...
That's the way we're recommending it. People can...
So, but you can kind of mix it in. Like if you're writing, some new code, but your code base already has some CUDA, you could write the new code and use the NVC compiler?
Yes.
Okay.
I'm curious what kind of challenges you hit. I'm trying to visualize, okay, you have to compile this function for offloading to the GPU. Then when you go to actually execute the algorithm, you've got your C++ memory, whatever that is in whatever byte ordering makes sense with whatever calling conventions make sense on this architecture, and then you have to do something different on the GPU. Is there a translation layer or something? How does that work?
Well, we've been doing GPU programming for a long time.
Right.
And so we basically pulled together technology that we already had. So our compiler, through the OpenACC support, already knows how to generate code for the GPU. We know how to identify functions, and we have our GPU code generator for them. So those functions get fed to both the CPU and GPU code generators.
Okay.
And then the unified memory that gets the heap automatically shared, that's been available in CUDA and OpenACC for several years already. So that's a well-known technology.
Okay.
So it really was piecing them all together and writing the header files that calls the right things to get to launch your kernel on the GPU.
With the important key being that it looks to the user like magic.
Right.
Right.
Yeah, so there was quite a bit of work of piecing it all together, getting all these pieces together, but but most of the really big chunks were already existing stuff that just had to be adapted.
Okay.
Okay. So David, we mentioned in your bio that you've been a member of the ISO committee since 2018. Do you want to tell us a little bit about this paper you're working on about floating point types?
Okay. Right, 'cause this is one of things Nvidia wants in the standard, because 16-bit floating point types have been out there for a while. People are using them, and there is hardware support for them on GPUs, on Nvidia GPUs, and some ARM CPUs, and some other hardware out there. And people want to use them. 16-bit floating point is really small, and there's limitations, and you don't want to use it generally.
What are the use cases people are using it for? Sorry.
I'm not a math expert, a math programming expert. So I don't have a lot of experience, but I think if you have lots of data, the amount of storage becomes an issue, right? 16-bit floating point is less storage.
Right.
But if you have lots of data and you're more interested in the averages or in the trends, and you don't need precision in every single data point, then this smaller, less precision value may be useful. It may be a good space trade-off.
Okay.
Right, the space you save may be a good trade-off. So yeah, there's these people are using 16-bit floating point, but there was no good way to do that. You can't do that in standard C++. Standard C++ only has 3 floating point types: float, double, and long double. No provisions for more. And by convention, right, float and double are pretty much locked into 32-bit and 64-bit. If you changed float to be a 16-bit type, people would scream it. Your users would scream at you.
It might break some existing code.
So this paper this proposal is an effort to expand the standard's ability for floating point. So the paper is titled Extended Floating Point, and so we are proposing a way to allow compilers to define additional floating point types. These would be optional and implementation defined.
Okay.
But we specify the rules for how all these floating point types have to interact. So if your implementation defines a couple 16-bit floating points and 128-bit floating point type, these are the rules for implicit conversions, how they convert with each other, how overload resolution works, how your arithmetic conversions, so your math works, what the resulting types are. And then the second part of the paper proposes some standard names for well-known types, well-known layouts.
Okay.
So we are proposing standard names for IEEE 16-bit, 32-bit, 64-bit, and 128-bit, and for bfloat 16. And that is, bfloat 16 is IEEE 32-bit with 16 bits of the mantissa just chopped off.
Okay.
And that is in use. So there's actually 2 16-bit floating point types that are out there in use with hardware support, the IEEE 16-bit and this bfloat 16.
And so just to maybe clarify for me and for the listeners, IEEE floating point that's what, 754 or something like that?
Yeah, that was like the original standard number.
Oh, okay. That's what we think of when we think of floating point. That's what our FPUs and our general purpose sorry, in our CPUs, whatever, in our general purpose computers generally work with.
Yes, that's what the vast majority of hardware out there is now IEEE.
Okay, so when you said this B float chops off 16 bits of the mantissa, like I cannot visualize what that means.
What does that mean?
Trying to remember how many bits are in there. There's normally IEEE 32-bit, if I'm remembering right, has 8 bits uses 8 bits for the exponent, 1 bit for the sign bit, and then 23 bits for the mantissa.
Okay.
And bfloat 16 just gets rid of 16 of those bits, so it only has 7 bits for the mantissa.
And the mantissa,
but it still uses 8 bits for the exponent.
Okay. Weird.
Yeah, so it's very, very low precision.
Low precision, but high.
But you have the same range.
The same range, right.
As 32-bit.
Okay. So who uses that?
I don't know exactly who it is, but again, that's actually maybe a good fit for this case where you have lots and lots of data, but you're only interested in sort of averages and trends.
Okay.
So you don't need the precision on every data point. You just need to know right what the trends are.
Right. Okay.
Okay. So this paper is in its 4th revision. Is it going well through the standard? Do you expect it to get into C++23?
I am hopeful that it will get into C++23.
Okay.
I guess with our slowing down, it's a little less likely, so it's definitely not guaranteed.
Sure.
It's not on not on the official priority list of things to do. So, but yes, it is making progress. There will be a couple more revisions. There's still more work to do. But the language rules for how these types interact are mostly worked out.
Go
ahead, Jason.
On a half serious, half joking note, if you're adding 1632, 64, 128, why not float 8?
Because people aren't using that.
Okay.
Out in the world very, very much. I have heard about an 8-bit float. No, it's not what I've heard of. It's not your usual IEEE. It's not similar to the IEEE types.
Okay.
It's something completely different.
No,
it's not widely used. But a compiler could support it as an extended floating point type. It just wouldn't have a standard name.
Right.
And we would have the rules there for how it would interact with the other floating point types.
Okay.
What type of work is still to be done on the paper?
To finish up, get consensus on how overload resolution should work, and then there's a bunch of library work to do. So we're proposing adding overloads or template specializations for all the extended floating point types in a bunch of places. So we have to figure out exactly which places we should do that and what exactly those mean.
I am curious
especially which sort of I/O should we support for extended floating point types, and then we have to pick the actual names. So we've proposed the types that will have standard names, but we haven't settled on what those standard names are yet.
You mean like short float or something like that, or?
Short will not be in there. There was an earlier proposal of just adding short float as a floating point type, and that failed, and then led us to be this more expansive one that allows more extensibility. So like one of the proposals is name it std float 32T. So some people want sort of IEEE in there, or actually IEC is where the formal name of what this layout is. So like IEC something in there. So there are several different Right, several different proposals out there. I'm not worried that we won't be able to agree on something. We just haven't done the work to come to that agreement on what these will be named.
I could see the argument for wanting the IEC or IEEE in there.
Yeah.
So I'm curious because something that's always kind of annoyed me with the standard is if I add two 8-bit values, I get back a 32-bit int because of integer promotion rules. And you were just saying a large part of this paper is describing the rules between these floating point values. What happens if I add two float 16s?
You get a float 16.
Ooh.
And that matches the current floating point behavior. Right now, if you add two floats, you get a float.
Oh, it doesn't automatically get promoted to the default of a double in that case.
Yeah, there are some places where float promotes to double.
Okay.
Right, that's preferred during overload resolution, for example, over a standard conversion. But in arithmetic, it doesn't. Floating point arithmetic does not repeat the integer arithmetic of everything promoting to int.
Sounds great.
And so we will preserve that behavior.
Okay. Jason, anything else you want to go over?
Just curious what things you are looking forward to in C++23 besides this floating point support to help with your parallel stuff.
Well, yes, we're pushing, and what NVIDIA's goal is standard C++ on GPUs. So part of that is expanding the standard.
Right.
In ways that is more GPU friendly. So the big one in there is executors, which, to greatly oversimplify it, is a standard way to control how and where your code gets run.
Right.
And so once executors get in, it will be easier to do some fine-tuning of how you want this to run on a GPU. You can specify, yes, I want this chunk of code to run on a GPU with certain properties. So yes, we are very excited about executors.
And does that
getting in.
Look like executors is on track for C++23, hopefully?
It is one of the top priorities. And
okay.
Yes, it is making progress. It's now it's in library evolution. And it's had a lot of virtual meetings have been devoted to reviewing that.
Awesome.
And improving it.
Right. And there's other features that are kind of waiting for executors too, right? Like networking,
yes.
I believe. Yeah.
Right.
Okay.
And the other area that we are working on that'll help GPU programming is linear algebra. Specifically, there's a proposal to have a C++ interface for BLAS, which is basic. I can't remember what it stands for. The LA in there is linear algebra.
Linear algebra system. Let's just,
okay.
I don't know. Yes.
Which has been around for many decades. It was developed for Fortran many, many years ago and has become a standard. But its interface is ugly, hard to use, very Fortran or C specific. And so there's a proposal underway to provide a C++ interface for that functionality. So some form of BLAS is used very widely in scientific computing.
Right.
And there's lots of ports to it to various. It's something that parallelizes as well. So there's lots of implementations of BLAS for multi-core CPU or for GPU. And we want to have a better interface for it, so it's much easier to use from C++.
Awesome.
Okay.
I did not know anything about that being worked on.
That's something that likely will not make C++23.
Okay.
Because it wasn't near the top of the priority list.
Right.
But there's lots of different people working on it. We're working in conjunction with the national labs on this. So I'm sure it will happen, just not sure when.
Right. Okay. Well, David, it's been great having you on the show today. listeners who are interested in getting started with the NVIDIA compiler, where should they go?
Go to the blog post that you will have in the show notes.
Okay.
That we talked about. That's the best description of it and has links to how to download the product and a getting it started section.
Sounds great. Thanks for coming on the show.
Thank you for having me.
Thanks for joining.